Hello. Today we're going to find the focal length of a converging convex lens and a diverging concave lens. Now we know that light is nothing more than an electromagnetic wave. It constitutes a very small portion of the electromagnetic spectrum, and these waves are sensitive to the eye, and that's where light comes from. So today we're going to see how these converging and diverging lenses can bend those waves to focus light. For this experiment, you will need some sort of light source, a converging convex lens, a diverging concave lens, and a white screen. You will also need some sort of measuring scale. You can see on this optics bench, this has one built onto it. And you can also see that we have a second screen with a small hole in it. This is just to limit the number of waves that's shining through the lens so that we can get a more focused image when it hits the screen. Before we begin our experiment, I'm going to tell you exactly how a concave and convex lens work. First, for a converging convex lens, the lens is curved outward. So when light waves hit the lens, it bends the light waves inward. The point where these light waves meet is called your focal point. For a diverging concave lens, the lens is curved inward. This refracts the light waves outward. To find the focal point, you can see if you were somehow able to take the new direction of these light waves and send them back through the lens, the point at which they would meet would be your focal point. The focal point, as you'll see in a minute, is the point at which we'll get the most focused source of light. Now, to begin our experiment, we're first going to find the focal length of the converging lens. So first to begin, we're going to have two variables when finding the focal length of our lens. We're going to call the distance between the light source and the lens U, and the distance between the lens and the screen V. Now to begin, we're going to adjust our lens at a fixed point on the meter stick. So here we have 65 centimeters, and our light source is at 110 centimeters. So our U value is going to be 110 minus 65 centimeters. And now we're going to adjust our screen so that we get a focused dot on the screen. You can see as I begin to move too far away, the light begins to fade. And as I come close, it begins to blur. So where we get our smallest and most focused dot, we found is at 15 centimeters. So our V value is 65 centimeters minus 15 centimeters. To find the focal length of a converging lens, we have this focal length formula. 1 over F, your focal length, equals 1 over U plus 1 over V. And with some simple algebra, you can rearrange it and see that F equals UV over U plus V. So our U value 45 centimeters, our V value 50 centimeters. Using this formula, we get a focal length of 25 centimeters for our first trial. We will do the same trial 4 more times. This time, we're going to adjust our lens to be at 60 centimeters and then adjust the screen accordingly until we find that focused dot. We found that the most focused dot lies at 26 centimeters. So our new V value is 60 minus 26 centimeters, and our U value is now 110 centimeters minus 60 centimeters. Once again, adjusting our lens, this time to 50 centimeters. We move the screen accordingly until we find the focus, which lies at about 26 centimeters again. This time, adjusting it to 50 centimeters. Focus lies at about 24 centimeters. This time, to 45 centimeters. And our focus lies at about 21.5 centimeters. Now that we have all of our U and V values, we calculated each focal length for each trial, and taking the average, adding all 5 of these up and dividing by 5, we found that the average focal length for the converging lens was 19.9 centimeters. And now to find the focal length of our diverging lens. For this part of the experiment, you'll need all the same materials, except this time on the optics bench, you'll need both the converging lens and the diverging lens. The reason we use both lenses is because, as we saw before, a diverging lens would diverge these light rays outward, and there's no way to reflect the light back to find this focal point. So, if we have both the converging and diverging lens, the light will hit the converging lens first, which will converge the light rays before it hits the diverging lens. And then, as you can see here, once the converging rays hit the diverging lens, the rays will diverge a little bit, meaning the angles won't quite be as steep, but they will still be acute relative to the beam of light. And that will give us a focus. So, we just set our light source and converging lens at a fixed point. Here, we'll set our converging lens at about 80 centimeters. Our light source is still at 110 centimeters. And we can put the screen really anywhere on the bench. We're going to put it at 40 centimeters. And now, we just move the diverging lens accordingly until we find a focused image. Unlike the last part of our experiment, it's not going to be a perfect circle, but we just have to find where the image is the most clear. I'm not sure how well you can see on the camera, but this is the position where our image is most clear. So our diverging lens sits at 60 centimeters. Our formula to find the focal length of a diverging lens is this right here. 1 over f, which is your focal length of the diverging lens, equals 1 over d, which is the distance between your diverging lens and the screen, plus 1 over f prime. F prime just means the average focal length that we found for the converging lens. So again, using some algebra, we get that f, the focal length of your diverging lens, equals distance times focal length of converging lens over d plus f. So using this formula, we take 20 centimeters, the distance between our diverging lens and the light source, times 19.9 centimeters, our calculated value for the focal length of our convex lens, divided by the 2 added together, 39.9 centimeters, equals 9.97 centimeters. And since we've been rounding to the nearest tenth, let's leave it at that. So we'll take 10.0 centimeters. And the focal length of a diverging lens is actually said to be negative. This is because, as we saw in our illustration, the focal point of a diverging lens actually sits behind the lens. It's between the lens and the light source. So all you do is put a negative sign in front of your calculation, so negative 10.0 centimeters. So our final answers. The focal length of our convex lens we found is 19.9 centimeters, and the focal length of our concave lens is negative 10.0 centimeters. And now for our final step, we want to find the percent error of our calculated values. To find the percent error, you take the absolute value of this fraction here, you take your calculated experimental value minus the actual focal length of the lens divided by the actual focal length of the lens times 100%. The actual focal length of the convex lens we used was 22.1 centimeters, and the actual focal length for the concave lens that we used was negative 16.4 centimeters. So using this equation for both, we get that our percent error for our calculated value of the focal length of the convex lens was 10%, and our percent error of our calculated value for the focal length of our concave lens was 39%.